17 2. Heat of formation, heat of combustion, and Hess's law. So, heats of formation. Okay. Now, first of all, we need to define something called a standard state. Okay, note this is different than standard temperature and pressure. Okay, standard state temperatures are not 0 degrees Celsius; it's 25 degrees Celsius. Okay, the standard state pressure is the same as the other standard pressure, 1 atmosphere. But remember this when they talk about standard state: 25 degrees Celsius. Okay, now. The molar heat of formation. Again, you see the term molar, so that means we're talking about 1 mole. Okay, so what is the molar heat of formation? It is the delta H. Okay, remember this basically means it's the heat of reaction, the enthalpy change for the reaction. Okay, but it's for a specific reaction. This reaction is when 1 mole of the compound, 1 mole of a substance, is formed from the elements in their standard state. Okay, so the elements have to be, when we talk about what your reactants are, it's the elements in whatever state they are in at 25 degrees Celsius and 1 atmosphere of pressure. Okay, and those are always the reactants elements. And your product has to be only 1 mole of the substance that we're talking about. Okay, the heat of formation symbol, delta H F naught. Okay, and you can find these in table A14 in the back of the book, page 901. Okay, now what do all these things stand for? Okay, well, F, you know, is going to stand for formation. Okay, delta H, you know, is the heat of reaction. And this naught right here means we're working at standard state. Okay. If you don't include that 0 right there, then basically that just means it's the heat of formation at some other temperature and pressure. But the values in the book are for specifically 25 degrees Celsius, 1 atmosphere pressure. Okay, so here is a reaction. Okay, hydrogen gas plus oxygen gas yields water gas, water vapor. And the delta H, the naught, again, doesn't mean anything special except it's at 25 degrees Celsius and 1 atmosphere. Okay, so the heat of reaction for this reaction is negative 483.6 kilojoules. So again, the negative means it's exothermic. Heat is a product of this reaction. Okay, now if you look up the heat of formation for water, it's negative 241.8 kilojoules. Okay, now notice what's the relationship between this value and that value. Okay, well, it looks like it's about half as much. Okay, so why is the heat of formation of water negative 241.8 and not negative 483.6 kilojoules? Okay, simple reason. Remember, let's go back and look at the definition. Okay, molar heat of fusion, we have to make 1 mole. Okay, here in this reaction, we're making 2 moles. So the heat of reaction, the delta H for this, is not the heat of formation. Okay, now heat of formation for any element in its standard state is 0. Okay, why? Because by definition, you have to make 1 mole of the substance from its elements. Okay, so if you make 1 mole of an element from an element, did anything happen? No. So the heat of reaction is basically 0. Okay, so that's true for any pure element. That's why you won't find them listed in the table. Okay, so what should the actual reaction be to make water? Okay, well, it should be, well, we have to make 1 mole of water from its elements, H2 and O2. Okay, but you cannot put a coefficient here. The coefficient has to be 1. So to properly balance this reaction, you have to use a 1/2 here. Okay, and you can't go and double it and get rid of it, because otherwise the delta H for this reaction is not going to reflect making 1 mole of the compound. Okay, so notice if 2 moles creates 248.6, then the delta H for this reaction must be half as much, because I'm only making 1 mole. So that's going to come out to be negative 241.8, which is half as much of that. Okay. Whoops. Half as much on the top will give you that much. Okay, so write heat of formation reactions for each of these compounds. Okay, let me start you off with the first one. So, CO. Basically, you have to make CO from its elements. Okay, the elements are C and O2. Now, when you balance it again, you cannot write a coefficient there. Coefficient has to be 1. Okay, so to balance it, we have to put a 1/2 here. So this is the heat of formation reaction for CO. For CO. Okay, we're not making CO2. Okay, now try the rest of these. Okay, pause the video, come back, and check your answers. Okay, so over here you're going to make NO2 from its elements. Be careful. Nitrogen is N2. Oxygen is O2. Okay, and make NO2. To balance it, you can only balance the left side. So this needs a 1/2 there. Okay, now you're going to make H2SO4, not from ions. You have to make it from elements. So elements are hydrogen, which is H2, sulfur, and oxygen, which is also O2. Okay, so to balance it, you need 2 O's, and that'll balance it. Okay. Also another ionic compound, but heat of formation reactions are from elements. So we're going to make Na2C2O4 from the elements. Sodium is not diatomic, it's just Na. Carbon is not diatomic, oxygen is diatomic, O2. Okay. Balance it, 2 of those, 2 of those, and 2 of those. Okay. So these are all the reactions. So the delta H for this reaction would be the heat of formation of CO. Delta H for this reaction is the heat of formation of NO2. Delta H for this reaction is going to be the heat of formation of H2SO4, and same thing for this one. Delta H is the heat of formation of Na2C2O4. Okay, now heat of combustion. Okay, this is the delta H for a special type of reaction. It's a combustion reaction. Okay, now 1 mole of the reactant is what you have to make sure you keep. You can change the amount of, you can balance the amount of oxygen, but you have to make sure you keep 1 mole of the reactant. Okay, so this is given the symbol delta H naught C. C is just for combustion, and again delta H naught, just to heat a reaction at standard state. Okay, so what's the heat of combustion for hydrogen? Okay, well, you need to write the reaction for hydrogen burning. H2 plus O2 yields H2O. When you balance it, you cannot change that coefficient because we're talking about the heat of combustion for hydrogen. So this has to stay 1. So when you balance it, O2, you can change the amount of stuff you want on the right side in this case. That's fine, but you cannot change that one. Okay. Now, heat of combustion for hydrogen comes out to be negative 241.8. Where'd you see that before? That is also the heat of formation of H2O gas. Okay, why? Because they're the exact same equation. This is not only the heat of combustion reaction for hydrogen, it's also the heat of formation for H2O gas. So their delta H values will be exactly the same. Okay, now comes a fun one. Hess's law and heats of reactions. Okay, this is basically Hess's law. Remember this. Okay, now we're going to go about a roundabout way, kind of a long way, to show you where this equation actually came from. Okay, that symbol right there, whoops, that should be pointing here and not there. Okay, but these symbols, these are called sigma. Okay, and remember we saw sigma before, that's a lowercase sigma. This is the capital sigma. Okay, this means summation, or the sum of all the heats of formations of products minus the sum of all the heats of formations of your reactants. Okay, remember, these are in the table. Okay, and watch out. When you look in the table, those values are always per mole. So if a reaction says you have more than 1 mole of a product, you need to multiply it by the coefficient. Okay, now, what does Hess's law actually say? This is the actual definition of Hess's law. The heat of reaction is independent of the path that the substance took to be formed. Okay, what does that mean? Well, suppose you had a reaction like this. A plus C is going to yield D. Okay, and the heat of reaction, we'll call it delta H1. Okay, now, suppose we had a bunch of other reactions that we knew. Okay, E plus G gives us X plus A, 2A plus X gives us Y plus D, and then Y plus C gives us G plus E. Okay, Hess's law says that you can actually combine if these three reactions combine will give you this one, then all of these delta H's will be equal to that delta H. Okay. Now, what happens if you add all three of these together? It's just like adding together mathematical equations. Anything on the left can cancel out with anything on the right of the arrow. Okay. Think of these as like the equal signs. I got a G and a G. Okay. There's an A and an A here, but it's 2A and A, so I can only cancel out one A, and I still have one A left there. Okay. And a Y go away. So, and the X and the X go away. So what's left over? A plus C will yield D. Okay. So if I add those three equations together, I end up with the original equation. So the sums of these heats of reactions will equal that one right there. Okay. So the heat of reaction for the first equation is equal to the heat of reaction of the second plus the third plus the fourth. Okay. Now, how do we use that in a real equation? Okay, well, a couple other things first before we do that. Okay, notice if I double everything, the heat of reaction also doubles too. Okay, this is twice the amount of that, so H5, the heat of reaction for this will be twice the amount of that reaction up there. Okay, if I flip it backwards, instead of A plus C gives me D, D gives me A plus C. When you flip it backwards, the sign changes. The value will be exactly the same. Okay. Now, use Hess's law to find delta H for the following reaction. Okay. So, the long way. This is how you do Hess's law. Okay. For each reaction, or for each compound that we see, this is a compound, this is a compound, this is a compound. Write heat or formation reactions. Okay, so this is what we do. Here's our equation. Okay, so find our first compound right here, CH4. Okay, write a formation reaction. You have to make it from the elements C plus H2. Okay, and then balance it. So that's 2. Okay, so the delta H's for this entire reaction is going to be equal to, by definition, we are making the formation of CH4. Okay, write all these things out, because when you have to do this on your homework and on the test, you have to do it like this. Okay, so make sure you do everything I'm showing you here. Don't get lazy. Okay, next thing, O2. We don't need to do it because it's not a compound, it's an element. Okay, our next compound, CO2. So we need to make that from its elements, carbon plus oxygen. Okay, I don't need to balance it anymore. And the delta H for this reaction, by definition, is going to be the heat of formation of CO2. Make 1 mole of CO2 from its elements. Okay, and we have H2O also. Okay, so let's go make H2O from its elements, H2 and O2. Okay, and the heat of formation of H2O is going to be, or the heat of reaction for this is the heat of formation of H2O. Okay, now the next thing we have to do is manipulate these reactions 1, 2, and 3, so that if I add them up, I end up with the original equation. Okay, now notice CH4 is on the product side, but when we look up here, CH4 is on the reactant side. So I need to take equation number 1 and flip it around. Okay, so when I flip it around, CH4 yields C plus 2H2. Okay, now what just happened to the delta H? When I flipped it, the sign became negative. Okay, so it's now the negative heat of formation of CH4. Okay, so because we manipulated that one, let's ignore it, because that is now going to be this equation right here. Okay. take a look at the equation. Okay, I have 2 moles of H2O. Right here, I only have 1 mole of H2O. So, how do I make that? And the H2O is on the correct side. CO2 is on the correct side. Okay, they're products, and they're products here in our reactions. So, how do I get it to look like the original up here? Okay, well, I need 2 of everything. So, 2 H2s plus 2 O2s will yield 2 H2Os. Okay, and since I doubled it, this also has to get doubled also. So, the heat of formation is now going to be the heat of formation, or heat of reaction for this is the heat of formation times 2. Okay, we change that one, so this will go away also. Okay, and the CO2 looks like it's what it's supposed to be. So we'll just rewrite this one right here. C plus O2 will yield CO2, and the heat of formation is, or the heat of reaction is the heat of formation of CO2. Okay, so we'll ignore it so we don't get confused. Okay, now, what happens if I add everything up? Okay, well, take a look. CH4 on the left side, no CH4 on the right side. Okay, those are the heats. I have a carbon on the right, I have a carbon on the left. I got 2 hydrogens on the right, 2 hydrogens on the left. Okay. Whoops, this got messed up. That should have been originally 1/2 O2, so when we doubled it, it should have just gone to 1 O2. Okay, so an O2 and an O2 will give me 2 O2. Okay, I can't cancel anything else out anymore. On the left side, I have CH4 plus 2 O2 will yield 2 H2O plus CO2. Okay, and I end up with the equation that I'm looking for on the top, right up here. Okay, now, what does all this have to do with everything? Well, since I added up all these equations, we'll call them A, B, and C, then that means the delta H for all these reactions has to be equal to the sum of all these things. Okay, so if we put it in there, it turns out to be delta H naught will equal negative heat of formation of CH4 plus 2 times the heat of formation of H2O plus the heat of formation of CO2. Okay, so that is what the delta H will end up being. Okay, now that's the long way to do it. Okay, the short way would have just been use the sum of the heats of formations of the products minus the sum of the heat of formation of the reactants, meaning just would have been equal to the sum of the heat of formations of CO2 plus 2 times the heat of formation of H2O minus the heat of formation of CH4. Okay. You can add in the heat of formation of O2, but don't forget, this is equal to 0, so we can just ignore it. Okay. So, heat of formation of CO2 plus 2 times the heat of formation of water minus the heat of formation of CH4. Go back, take a look. Heat of formation of the CO2 plus 2 times the heat of formation of the water minus the heat of formation of CH4. Okay. So this gives us the exact same thing. Okay, here's your review question.